This video is part 2 of mechanical properties of materials. Part 2. In the last video, we defined a few different properties of materials, and they all began with what was a tension test, right? And we defined engineering stress as the applied load divided by the original area. We defined engineering strain as the change in length divided by original length. We defined another property, Young's modulus, by saying that it is the relationship between stress and strain at very small strains when the material is linear elastic. So this was one of our key equations. We call it Hooke's law. And E was our Young's modulus. And we had one more new material property that we defined, which was Poisson's ratio, and that is negative the lateral strain divided by the longitudinal strain. This guy was what we call Poisson's or Poisson's ratio. A couple more things about these tension tests. So when we conduct a tension test, we can plot a stress strain curve. And we talked about last time that it goes up and has this linear region before departing from linearity. And then some other interesting things happen, but in the end, we typically have strain hardening and then we fail. And the reason the curve looks like this at the very large strains is because we're plotting engineering stress, which is force divided by original area. So this guy right here is what we get when we plot engineering stress. Well, we now know about Poisson's ratio. You remember what Poisson's ratio means? Is if I'm pulling on a strip of material along its length, it is going to get longer, but it's also going to get smaller. It's going to contract so that our original area, this big black area, A naught, as the test goes on, as we pull harder and harder and this gets longer and longer, the current area, the area of the blue square, is going to be smaller. So remember, stress is force over area. We decided to define engineering stress as force over original area, but as the test goes along, the original area gets smaller. And the more you strain, the smaller that area gets. So if we instead plot stress where during the test we keep updating the area with the current area, we get a different quantity called true stress, which that's force over current area. And I want to show you what happens when we do that. When we do that, let's plot it in blue. Instead of decreasing, it actually keeps increasing because that area is getting smaller, areas on the bottom of the fraction, so that actually shoots the stress up higher. So this guy is the way true stress would actually behave. Something I want you to be aware of. If you've taken material science class, you probably already knew that. In this class, we are limiting ourselves to this little tiny region at the beginning where we have linear elasticity and Young's modulus. I'll remind you from last time, how far can we go along that stress strain curve while we still decide that it's okay to use all the equations we're going to develop over the next few weeks? Well, we've decided that we're going to define the yield stress by coming over here a very small strain. Specifically, we're coming over here 0.002, which is also 0.2%. And we're going to draw a parallel line, and wherever it intersects the stress strain curve, that is what we're going to define as our yield stress. And in this class, we will never go past the yield stress because we are assuming that all strains are small, all deformations are in the linear elastic range. This 0.2% means we're not technically completely perfectly linear, but with an experimental error, we're pretty linear. And that 0.2% offset strain was defined by people who wanted to be able to take massive amounts of data and always arrive at pretty much the exact same yield stress. So that works pretty well. So we have yield strength, which is an important property. I want to talk about for just a minute, what happens if I go and collect stress strain data from a bunch of different, say, steels. So same material family, but maybe I've got low carbon steel, high strength steel, spring steel. Well, a really soft steel might look like that. One that's got a little bit higher, better heat treatment, more alloys. You actually end up getting a whole family of curves like this, where down here at the bottom, we might have a mild steel. Up at the top might be our very strongest spring steel. And so here's the interesting thing. Because their underlying microstructure of steel is the same no matter what the steels are, and the only difference here is how we might have alloyed it, work hardened it, heat treated it. The material actually all has the same Young's modulus. See how that linear elastic part here at the beginning? Same slope. Because that slope is really based on the underlying atomic structure of steel. Now, all the alloys that you put in there, the work hardening that you do, the heat treatments that you might do to it, tend to change how long it stays linear elastic before it begins to yield. So all of these curves that's not very good grammar. They all have the same Young's modulus. For steel, that is 29 times 10 to the third. I don't want to write this wrong. Times 10 to the third KSI, or actually I was going to write it as 10 to the sixth PSI, which is approximately 200 gigapascals. But the yield strengths are very different. In this class, both numbers are important. Young's modulus is important for relating things like stress and strain and loads to deflections. Yield strength is important for knowing how much stress can we apply to this structure before we expect it to start failing. So if you look this up in the back of the book and you look at different steels, you're going to find very similar Young's modulus values, but very different yield strength values. The other thing to mention about stress strain curves is the stress strain curves I've been drawing have really been largely for ductile materials, but sometimes we have to deal with brittle materials. So let's define ductile versus brittle materials really briefly. Ductile is the idea of something that can be deformed for quite a while before it completely fails. It has a true yield stress. Brittle is going to be a material that tends to snap and break more easily. My example last time was, what if you pick up a piece of wood, a stick, and you try to break it? Well, if it's very wet wood, is very ductile, can be very hard to break, whereas dry wood tends to be extremely brittle. Sometimes changing the temperature will change something from ductile to brittle. If you freeze something, it will be like the plastic containers that you store your leftover food in. If you freeze it and then pull them out of the freezer and drop it, it's amazing how that plastic fractures when it's cold, whereas it might have been just fine when it was warm at room temperature, heated up in the microwave. So what is a ductile versus a brittle stress strain curve? How is that different? Well, the ductile one we've seen already starts doing something like that. And then if it's engineering stress, it eventually fails like that. Brittle is going to, we'll draw brittle in blue, is going to follow the same kind of curve, but right about here is going to break. Typically, you don't even see any yielding at all. So a brittle material has no yield strength to speak of. It tends to have like an abrupt early fracture. A couple of brittle materials we use a lot in engineering are concrete and cast iron. And what you find is that they have actually much better properties in compression than tension. Much higher compressive strength. Than tensile. So that's kind of important to know. And how do we define ductility? We define it by something called percent elongation. So percent elongation, which guess what, is just percent strain. It would be change in length divided by original length times 100%. And for most steels, like mild steel, that percent elongation is in kind of the 40 to 60% range. So you can elongate it quite a bit before it fails. Brittle materials is going to be much smaller than that. Tiny. We're talking, less than 1% elongation for a truly brittle material. We've got one more material property, then we'll do a couple of examples, and then we will be done with this chapter. So our next material property relates to shear. So we've talked a lot about tensile tests, which are used to define Young's modulus. Well, if you do a shear test, you can define something called a shear modulus. So remember, we had Hooke's law for tension. Let me get rid of that. Hooke's law for tension said normal stress was Young's modulus times normal strain, right? That was Hooke's law for tension. Well, there's a similar law for shear. So shear, we define shear stress. You guys have seen this before. Average shear stress is going to be shear force divided by area, where if we think about shear as being, a force like that acting over an area right here. You kind of see that. That's if I'm looking at the area on the side, it's not the area in the front, it's the area on the side. We can take that shear force divided by area and get a sense of average shear stress. We're also going to use shear strain. This guy is shear strain. Now, the way we define shear strain is it is an angle change in radians from something that was originally a 90-degree angle, which is better drawn than written out. So if I have something that's 90 degrees and I shear it like this, it is going to change shape. It's going to get higher on this side, lower on the other side. And so our shear strain, look at an angle that used to be 90 degrees. So for example, this angle used to be 90 degrees. It is now a little bit smaller than 90 degrees. So our shear strain is going to be this little tiny angle in here. I drew it in a very exaggerated way. We're talking about tiny strains, tiny angles. But that angle right there would be gamma. So originally 90 degrees, how much did the angle change? It should be a small change, and that's how we define gamma. So if we have shear stress and shear strain, we can relate them using a shear Hooke's law. And it looks like this. Tau is equal to G gamma, where G is what we call the shear modulus. And let's talk units for a second. Shear stress is in units of PSI or pascals. Shear strain is in radians, which is dimensionless. And so G is in also units of PSI. So we have three main material properties. Those material properties are Young's modulus, shear modulus, and Poisson's ratio. It turns out they're all related. There is a fabulous formula that if you take advanced strength of materials later on in life, you get to learn how to derive. Shear modulus is Young's modulus divided by 2 times 1 plus Poisson's ratio. That's great. So if you ever only knew 2 of them, you could solve for the third one by using this equation. Let's do 2 examples. First example looks like this. We have a beam that is supported by a bar that's pinned to it on the left that is pinned to a ceiling. And then we have a post over here that's fixed to the ground somehow. This is point A and B for the bar on the left. This is C and D for the post on the right. And we have a downward applied force P in the middle. Let's get some dimensions. This is a 2 meter long bar. The distance from A to the applied load is 0.75 meters. I know it looks longer than that. This one's also 0.75 meters. And then the height of bar CD is 0.5 meters. We are given that the diameters of AB are 12 millimeters. The diameter of CD is 40 millimeters. And then we are also given information about the behavior of the material that bar AB and post CD are made out of. So the material looks like this. Here's a stress strain curve. And in tension, this material is weaker. In tension, it will break at 50, that doesn't look like a very good 5, at 50 megapascals. This is the tension curve. In compression, it can handle a lot more load. Here's our compressive stress strain curve. It can go all the way up to 90 megapascals. And the question is, find the maximum load P before anything breaks. So let's think through strategy here. I have a stress strain curve which tells me the biggest stress I can have in CD and AB. So I'll probably use that to figure out the biggest force I can have in AB and CD. And then I need to relate that somehow back to the applied load P. I like to do the statics part of problems first. So let's start with a free body diagram so that I can relate that applied force P to the internal forces in bar AB and post CD. So doing a free body diagram of AC, that's going to look like a rectangle with a downward force P. I'm guessing that member AB will pull up on it and CD will push up on it. And then right after free body diagrams, we do equilibrium equations. Let's try summing moments about point A. And I get that the force in CD times 1.5 meters minus P times 0.75 meters equals 0. So the force in CD should be P over 2. And then if I sum forces in the y direction, I get that the force in AB plus the force in CD minus P equals 0. So the force in AB is also P over 2. You might have been able to figure that out without writing the whole equations out, but we have a relationship now between the internal force in member AB and the internal force in member CD and the applied load P. So next, let's move on to calculating, getting an expression for the stress in each member. So let's first do stress in member CD. Member CD is going to be in compression, right? It's pushing up on the beam to support it. That's what this means right here, is that the CD is pushing up on the post, or on the bar, which means that the bar is pushing back down on member CD. It's in compression. So I'm going to set this equal to 90 megapascals, the most stress we can handle. I'm going to write megapascals as times 10 to the, not times 70, times 10 to the 6th. Pascals is a newtons per square meter. That equals force over area, which in this case is going to be P over 2 divided by pi times the radius squared. The diameter was 40 millimeters divided by 2, which gets squared. And now let me give myself just a little bit more space here. I'm going to multiply this by 1,000 millimeters per 1 meter, and then do it again. You could have just written this down as 0.04 meters if you wanted. to save yourself that step. The reason I want to do that is that then these 2 millimeters cancel the millimeters squared, and I'm left with meters squared on both sides of the equation, which will cancel. I'll get my force P in newtons. So rearranging all of this, solving for P, I get that P is 238,700 newtons, or you could write that as 238.7 kilonewtons. So that's how much force I'd have to apply in the middle of the beam to cause post CD to crumble and crush and fail. Let's check the other side, stress in AB. This one's in tension, right? Tension looks like this on my free body diagram. The arrow up means that member AB is pulling up on that end of the beam to support it, which means that the beam is pulling downward on member AB, putting it in tension. So I'm in tension. I want to use my tension curve, which means the max stress I can handle in this member is 50 megapascals. So let's write this as 50 times 10 to the 6th newtons per square meter. That's equal to F over A. The force is P over 2 again. And then the area is going to be pi times the radius squared. 12 millimeters over 2 gives you the radius. We square that, and I'll again multiply by 1,000 millimeters per 1 meter times 1,000 millimeters per 1 meter. And running through all of that, I get 11,300 newtons, which is 11.3 kilonewtons. That's what P is equal to. And this is going to be our actual final answer. This is what governs failure, because as I gradually apply more and more load, I'm going to reach 11.3 kilonewtons and bar AB is going to break. So we are never going to get to 238.7 kilonewtons. That post is way over designed really for the situation, is one way to put it. Let's do one more example where we actually use that shear modulus that we just talked about today. So in this example, we've got kind of a ceiling up here, and I have a couple of supports, and then we have a couple of rubber pads that are holding up this other bar. And they label this one in the middle A, this one over here B, and this one C. Let's shade in the rubber pads so you can tell where they are. These guys are made out of rubber. And I have a downward 50 Newton force being applied to member A. And the idea is that that's going to put those rubber pads into shear. It's going to tend to want to shear them downward, or shear them by the downward motion of that bar A in the middle. The rubber pads both have a width of 40 millimeters. And we also know that the rubber pads have a cross section that is 20 millimeters by 30 millimeters. That means that maybe the height here is 30 millimeters and then the width into the page is 20 millimeters, or the other way around. Doesn't actually matter which one is which. The overall cross-sectional area there is 20 by 30. And we are told that the shear modulus of the rubber is 0.2 megapascals. Shear modulus of rubber is way smaller than shear modulus of steel. Remember, steel is like 200 gigapascals. With this information, we are supposed to find the downward deflection of member A. So the idea is that A is, by applying 50 newtons of force to A, it's going to lead to some shear stress in the rubber pads on either side of it. That's going to cause these that are originally rectangular to deform downward like that. And we're going to use the stress and strain relationship with the shear modulus to figure out, and then the definition of shear strain to figure out how that translates into actual downward motion of A. So let's start with some free body diagrams. And I'm going to do a free body diagram more or less of block A, but if you want to think of it as we're cutting through just a little bit of the pad to expose the internal force in the pad. You can think of it that way. I'm actually going to draw it that way. So here's A, with just a little tiny bit of rubber pads on each side of it. And the downward force that's applied is 50 newtons. And so the upward forces that are resisting it would be our shear force in each pad. Call those V. Then immediately we do equilibrium equations. The only one that does any good for us here is not moment. Summing forces in the y direction has to be 0, and I get 2 times the shear force minus 50 newtons equals 0. So the shear forces are each equal to 25 newtons. That's how much shear force is in each of those pads. Next, let's calculate shear stress. To get shear stress, we need the tau is V over A. So that's going to be 25 newtons. And then the area is going to be our 20 millimeters times 30 millimeters. So you could write that as 0.02 meters times 0.03 meters. And if we calculate that, we get 41,667 pascals, which you could write as 41.67 kilopascals if you wanted. We have shear stress. Now we're going to use our new Hooke's law for shear, which says tau is equal to G gamma. Shear stress is shear modulus times shear strain. So solve for shear strain. Shear strain is going to be tau divided by G, 41,667 pascals. G is 0.2. I'll write it as times 10 to the 6th pascals. And this comes out to be 0.20833. It's dimensionless, so we'll call it radians. Just to remind us that it's not degrees. Shear strain is an angle, is a kind of a dimensionless angle, so we use radians rather than degrees. So what does that mean physically? Well, our rubber pad looks like this. Let's say we're drawing the pad on the right. If it was pulling upward on the bar, that means that the bar is pulling downward on it. So V is going to look like this in that rubber pad. So the shear stress, same direction. So the side on the right is going to stay put, but the side on the left is going to move downward. So let's kind of draw, it's going to go downward, downward. So the new shape is kind of this blue thing I just outlined. Where is gamma on this diagram? Gamma is the change in angle from something that used to be 90 degrees. So our 90 degrees is that black right corner right there. Right there is gamma. This width is 40 millimeters. Be a little clearer if I get rid of the squiggles in the middle. There we go, 40 millimeters wide with gamma right there. And what we were trying to find is this right here would be delta A. However far we move from here down to here would be the displacement downward that A is going to experience. So I have a little triangle. I know one side, I know the angle, it's a right triangle. I should be able to figure out the other side. So the relationship is that the tangent of gamma is, tangent is opposite over adjacent. So that's delta A over 40 millimeters. Oh, that's not too bad. Just make sure make absolutely sure your calculator is in radians and not degrees before you do that tangent. And if you do, you get that delta A comes out to be 8.46 millimeters. And there's our answer. There is another way that the book will often use, because that is 0.2 radians is a pretty small angle, and we're going to see even smaller angles in this chapter and going forward because we're dealing with small strains, linear elastic range, and all of that. So we will oftentimes instead use the small what's called the small angle approximation. I don't know why my pencil is doing that today, guys. Approximation. Small angle approximation says this. It says that the tangent of an angle, this is just annoying. Just erase it all. Small angle approximation says that the tangent of gamma is approximately equal to gamma. Thought I changed the settings so that it wouldn't do this anymore. Not sure what's going on with my pencil. So tangent of gamma is approximately equal to gamma. So if I use small angle approximation, then I would just have gamma is equal to delta A over 40 millimeters. Now, I think this strain of 0.2 radians is a little big to use small angle approximation, so I compared. If you use small angle approximation, you get something that is close, but not quite the same. You get 8.33 millimeters. So close. You're not terribly off if you use small angle approximation. The book will use it quite a bit when we're dealing with shear strains. But there is a little bit of error as the angle gets bigger and bigger. So, I mean, either of these answers is probably fine for this problem. I like to just go, I don't think finding a tangent is really difficult with our calculators. So I would go ahead and use the actual tangent of gamma, but just so you're aware that the book will sometimes just drop in a small angle approximation like that on you. Well, with this example, that concludes our lesson on mechanical properties of materials, which is the end of this chapter in our book.